definition. Now we'll go into the in-depth details of the second type of a photo detector, which is the internal photo detector. These photo detector can be classified into two types. One is the photo detector without internal gain, and the other is a photo detector having some internal gain. So the photo detector without internal gain is PN photodiode and PIN photodiode, and the photo detector with internal gain are avalanche photodiode and phototransistor. Now we'll go into the in-depth details of the first type of internal photoelectric effect detector. So PN photodiode is an optoelectronic sensor that is capable of converting an optical signal into an electrical signal that we know. It is designed by joining the p-type and n-type semiconductor. The incident light must fall on the depletion region for its proper operation. It works on the principle of electron hole pair generation. So in the figure, the PN junction is reverse bias, as you can see. It means the P side is connected to the negative terminal of the battery and the N side is connected to the positive terminal of the battery. So at the depletion region, this is the depletion region. The shaded region is known as the depletion region. Is formed due to this reverse bias. Hence, when these photons H nu, when this photons it is incident on the depletion region, the electron hole pairs are generated. So the electrons will be drifted towards the N side and the holes will be drifted towards the P side due to the electric field set up by the external reverse bias voltage. Hence, drift current will flow to the device, which is measured by using this microammeter. In order that the light penetrates deeply into the semiconductor material so that more electron hole pairs will be generated, a wider depletion region is necessary. Hence, to achieve this, the n-type material is doped so lightly so that it can be considered intrinsic. As we know that intrinsic means a semiconductor in its pure form. So semiconductor in its pure form, it means it is not it's not a doped semiconductor. That means it is not mixed with any impurities, but it is a semiconductor in its pure form. So this n-type layer at the middle is doped so lightly so that it can form an intrinsic layer, and the p and n-type at the side they are doped heavily. They are doped heavily in order to make an ohmic contacts or to make a low resistance contact. As we know that when a semiconductor is doped heavily, the conductivity of that semiconductor increase, but the resistance it decrease. So these two semiconductors at the sides are doped heavily. This creates like some sort of a PIN structure. Okay. So this PIN photodiode is a modified version. We can say that it's a modified version of a PN photodiode, based on the fact that it can have a wider depletion region, and it can accommodate more photons at the depletion region, and hence more electron hole pairs will be generated, and this will ultimately contribute to the increase in the drift current. So in this figure you can see the PIN structure. So in the middle we have the intrinsic layer, at the side we have the P and N type semiconductor. So as we can see, the presence of this intrinsic layer, the center, at the middle, it will create a wider depletion layer. So a wider depletion layer means as you can see, that means we can accommodate, that means we can have more incident photons. So when we can have more incident photons, then there more electron hole pairs will be generated. So as a result, the drift current increases rapidly. about the next type of a photodiode, which is known as the avalanche photodiode. This photodiode is also commonly abbreviated as APD. So this photodiode, it has a more sophisticated structure than a pin photodiode. It is sophisticated in the sense that this particular photodiode, it have an internal gain. It works on the principle that a single electron hole pair known as the primary carriers, when they acquire sufficient energy, then they will create another electron hole pair, and the process is commutative. This process is similar to a chain reaction, and it's known as the process is known as impact ionization. The most common APDs are made from silicon. So this particular APD is known as a rich through APD or rich through avalanche photodiode, as the light enters through the this silicon layer. In this figure, the highly doped region denoted by P plus and N plus. This highly doped region, they sandwich an intrinsic layer at the middle. So this intrinsic layer is also known as the depletion region. The depletion region is also called as the absorption region, because light is absorbed in this region and free electron hole pairs are generated here. The region between the P and N plus, the region between the P and N plus here, the P and N plus is known as the avalanche region. So this is the avalanche region between the P and N plus. This is known as the avalanche region. Now let us see how this avalanche process takes place. The light that enters through the N plus region, P plus region, and then it goes into the intrinsic region, and it is absorbed there, and hence electron hole pairs generated. Under the strong electric field which is set up by the external reverse bias, the electrons will be drifted towards the anode, and the positively charged holes will be drifted towards the cathode. Since in case of the holes which is being drifted towards the cathode, there is no avalanche region, so no avalanche process takes place. On the other side, these electrons, which are being attracted towards the anode, they encounter this high electric field region known as the avalanche region. So in this high field region, the field accelerates electrons to such a high speed that it creates more electron hole pairs, and this process is known as impact ionization. So as you can see from this third figure, the electrons which is known as the primary carriers in this case, these electrons will strike this the electron hole, like the other electrons, and it will create even more electron hole pairs, leading to an avalanche effect. So this is how the avalanche process takes place in an avalanche photodiode. Avalanche photodiodes have a distinct advantage over photodiodes without internal gain for the detection of very low light levels often encountered in optical fiber communications. They generally provide an increase in sensitivity between 5 and 15 dB over pin photodiode. However, APD also have several drawbacks, such as difficulties in their fabrication due to their more complex structure and hence increased cost. The other major problems is the gain of APD varies with temperature. This temperature compensation is necessary to stabilize the operation of the device. So in these problems that are encountered in APD are overcome by using a phototransistor. So a phototransistor is similar to a conventional bipolar junction transistor. The only difference is that the base is unconnected. In this device, the internal gain takes place due to transistor action rather than carrier multiplication. So as you can see in this figure, the base terminal is left unconnected and it is left open, unlike the conventional BJT, and incident photon is made to fall in the base collector junction. This is the structure diagram of the phototransistor. The device is a 3-layer device, and it is built on the N plus gallium arsenide substrate using liquid phase epitaxy. It consists of an N-type gallium arsenide collector, a layer followed by a twin P-type gallium arsenide base layer. The third layer is a wide band gap N-type aluminum gallium arsenide emitter layer, and the radiation is incident on the device. It passes unattenuated through the wide band gap emitter and is absorbed in the base collector depletion region. A large secondary photocurrent between the emitter and collector is obtained as the photogenerated holes and swept into the base, increasing the bias on the device. The different types of the photodetectors or the optical sensors that are used in our optical fiber communication system. Thank you.